Hi, I'm Frank Nielsen from Sony Computer Science Laboratories, and in this talk I would like to give a short tutorial on the principles and basics of information geometry, namely the Fisher-Rao manifolds and the dualistic structures of information geometry. I will illustrate these structures with applications ranging from statistical inference to machine learning. So, let us start by asking oneself, what is information geometry? Let us consider a family of parametric probability distribution, like the set of univariate normal distribution, which are parameterized by their means mu and variance sigma squared. The parameter space of this normal distribution in the upper plane lambda, and this family is called a statistical model. The basic question which motivated information geometry is to find geometric structures on this parameter space viewed as a smooth manifold. For example, we may ask how to smoothly interpolate between two distributions, or how to define a good notion of statistical distance between them. This statistical distance, which may not be a metric, allows us to define comparison predicates in algorithms, and so on. A puzzling question is to find if there are several ways to define geometric structures which are compatible with the statistical models, and if so, how can we choose the right one depending on the problem at hand? How can we say that a geometric structure is suited to a statistical model? This basic question can be tackled by looking at the invariance principles that shall govern the statistical model geometries and statistical distances. The first invariance principle is that, of course, the statistical distance shall not depend on the choice of the parameterization of the parameters of the distribution, since the family of normal is the same. Whether I choose mean standard deviation or mean variance or mean log variance, I can index distribution in their respective domains, but the statistical distances shall not be dependent on the parameterization when there exists a diffeomorphism between them. This clearly shows that the Euclidean distance between parameters is not invariant. Similarly, we should define interpolation paths which are independent of the chosen parameterization. This is the spirit of geometry. Information geometry relies on differential geometry to define structures on statistical models. We can interpret each parameter point on the parameter space of the statistical model as a geometry point lying on a manifold, and vice versa, when the model is said identifiable. That is, when there is a perfect smooth one-to-one correspondence between parameters and points. A manifold is an abstract geometric object which looks at infinitesimal scale Euclidean. We can index points on a manifold by an atlas of local coordinate charts, where the transition function between overlapping charts are smooth ordinary functions. In general, we need several charts to cover a manifold. For example, we need at least two charts for covering the 2D sphere. But information geometry usually uses a single global chart defining the atlas. Let us give a more refined definition of information geometry as a field which studies geometric structures on manifolds induced by statistical models and use these structures to solve various problems in information science. These statistical models can be parametric in classic information geometry or non-parametric, which is still an active research area. The geometric approach allows one to use the powerful language of geometry, like the notion of geodesics, balls, information projection, statistical curvature, and offers a calculus toolbox of differential geometry. A key concern is to define and study statistical invariance. Information geometry has unraveled a beautiful dualistic structure which can be used beyond the scope of statistics, like for example for studying optimization algorithms on manifolds. Historically, information geometry was born from the mathematical curiosity of using the Fisher information matrix of regular statistical models as a Riemannian metric and use the induced geodesic Riemannian distance as a statistical distance in statistics. The Fisher information of a random variable x following a parametric distribution p of theta is defined as the covariance of the score, where the score is the gradient of the log likelihood with respect to the parameter theta. Since the Fisher information is a score covariance, it is necessarily positive semi-definite. The Fisher information matrix, shortened as FIM, is said regular when it is defined and positive definite, and will allow us to define the Fisher-Riemannian metric. The FIM can be interpreted geometrically as a curvature of the log likelihood function at the maximum likelihood estimator, MLE. The curvature of a curve being the inverse of the radius of its osculating circle. In this figure, I illustrate the Fisher information for two different log likelihood curves. On the left figure, we see that the Fisher information is small because the radius of the osculating circle is large. It is a flat peak and variance of the MLE is large, meaning that we have low accuracy. On the contrary, on the right figure, the Fisher information is large because the osculating circle radius at the MLE is small. We have a sharp peak and the variance of the MLE is small, meaning that we have a good accuracy of the estimator. In many textbooks, the Fisher information is expressed using expectations instead of the covariance of the score. This is because the expectation of the score is 0 under regularity condition. More generally, we can use the so-called Bartlett identity to rewrite the Fisher information in two forms. Under regularity condition, which consists of allowing to swap integration with derivation order, we can express the Fisher information as the expectation of the score, this is the first form, or using the second Bartlett identity, we can find that the Fisher information matrix is defined as the negative of the expectation of the Hessian of the log likelihood. These two definitions allows us to consider empirical estimation of the field, which are useful for studying, for example, stochastic neural network models. Professor Mahalanobis has pioneered information geometry by using tensor notations for introducing his d-square statistics and the nowadays so-called Mahalanobis distance, which he called the generalized distance. Professor Mahalanobis was motivated by classification and clustering problems for analyzing groups of human skulls collected in various regions of India and China. The square Mahalanobis distance between two multivariate normal distributions, estimated from two groups with the same covariance matrix sigma, which is estimated by pooling the group covariance matrices, is defined as the following formulae, where the inverse of sigma is called the precision matrix. When the covariance matrix is identity, we recover the square Euclidean distance. Notice that the square Euclidean distance is not a metric distance because it does not satisfy the triangle inequality. In general, a divergence is a smooth dissimilarity measure between distributions which can be asymmetric or oriented and may fail the triangle inequality. The Mahalanobis distances have a neat interpretation as the canonical distances of vector spaces equipped with inner products. We can rewrite the Mahalanobis distance as an induced norm distance, where the norm is itself induced by a quadratic bilinear form. Q is a positive definite matrix. The inner product allows us to define angles between two vectors and therefore the notion of orthogonality between them, and also allows us to measure vector length. We shall see that the Mahalanobis geometry is a geometry of tangent spaces of manifolds. Consider now a smooth manifold and equip this manifold with a smoothly varying collection of inner products on tangent planes, the metric tensor G. A vector is a geometric object which can be manipulated by its components once a basis is chosen. A basis is defined as a maximal independent set of vectors. Given a local chart θ, we may choose the natural basis induced by the coordinate system. The inner product G of two vectors u and v can be calculated using linear algebra once we have chosen a convenient basis for getting the vector components and using the matrix of elementary inner products induced by the basis. For the manifold induced by a statistical model, we choose the Fisher-Riemannian metric expressed in the parameter θ as a Fisher information matrix. We can interpret the inner product of two vectors as the operation on the underlying statistical model. First, we use a natural basis, the score vectors, which are partial derivative with respect to the parameter components of the log likelihood. The inner product of the tangent plane at p of θ is then reinterpreted as the expectation with respect to the probability p of θ of the vectors. Since the vectors of the tangent plane have zero expectation, the inner product between u and v is reinterpreted as a covariance between the representation u of x, and v of x. We can visualize the Fisher information metric and the Kramer-Rao lower bound as the inverse Fisher information matrix on a chart by using the Tissot indicatrix. On the right map, I show the indicatrix for the Mercator projection, which indicates the local deformation by red ellipsoids. To visualize the Kramer-Rao lower bound for univariate Gaussians, we sample at each grid position mu sigma n identically and independently variate, estimate the mu sigma parameters via the maximum likelihood estimator, and repeat k times this operation to get the empirical covariance matrix of the mu sigma estimated parameters. They are shown here in black, and they are not necessarily axis-aligned ellipsoids. The manifold of a statistical model equipped with the Fisher information metric is called the Fisher-Rao manifold. Rao and Hotelling independently use the Riemannian geodesic length distance to define the statistical metric distance, nowadays called Rao distance. The square length element, ds square, is given by the following quadratic form. This length element is independent of the parametrization, and therefore the Rao distance is also independent of the choice of the parametrization. In practice, we first need to calculate Riemannian geodesics with boundary values, which is a complex task requiring to solve ordinary differential equations. Once the equations of the geodesics are known, we need to integrate the length element along with geodesics to get Rao distances. Both tasks are non-trivial. For example, we do not know the geodesics with boundary values nor the Rao distance in closed form between two multivariate normal distributions. Consider two parameterization by theta and eta of a statistical model P. The Fisher information matrix depends on the choice of the parameterization. We can transform the Fisher information matrix with respect to theta to the Fisher information matrix with respect to parameter eta by the following covariance matrix transformation, where we use the Jacobian matrix transformation of theta with respect to eta. We can show easily that the length element ds, whether expressed with theta or eta, matches. And thus the Rao distance does not depend on the parametrization. This is the first principle of invariance in information geometry. The Fisher-Rao manifold of the family of univariate Gaussian distributions is characterized by its metric tensor, which can be interpreted as a stretch Poincaré metric in the Poincaré upper plane. Thus, we get the Rao distance between two univariate Gaussians from the hyperbolic distance by taking into account the stretching on the variance parameter. The geodesics are either axis-aligned ellipsoid arcs with their centers on the x-axis or vertical line segments. Here, we show the Fisher information matrices with respect to three usual parameterization obtained from each others by covariance transformation. In general, the location scale families, which include the Gaussian family or the Cauchy families, yield hyperbolic Fisher-Rao geometry. We can always embed isometrically the intrinsic abstract Fisher-Rao manifold into Euclidean space as a surface. This allows to visualize the Fisher-Rao geodesics as trajectories which locally minimize length of that surface. For example, consider the family of Bernoulli distribution, which correspond to the family of all distributions for tossing a coin. The parameter space is a 1D probability simplex, shown here by the blue segment. If we map by the two square root transformation, Bernoulli parameters, we get parameters on the positive orthant of a circle embedded onto the 2D Euclidean plane. The Fisher-Rao Bernoulli manifold is shown by the blue arc. Using the Euclidean metric in this ambient space, we can thus deduce easily the Fisher-Rao distance between two Bernoulli distributions and recover the Fisher information of Bernoulli distributions. We can apply this Fisher-Rao modeling paradigm to large parameter spaces, like the parameter spaces of a neural network, like the multi-layer perceptron machine, which is a feed-forward architecture. We consider output being noisy by adding, say, a Gaussian noise to the output Y of the network. The neural manifold is a set of joint distribution of X and Y parameterized by the network parameters theta. Theta can be very large dimensional vector. Given the training set, we can show that maximizing the likelihood of such stochastic neural network amounts to minimize the mean quadratic error. We can also visualize the learning process as trajectories on the neural manifold, here shown by the red curve. However, in our setting, the Fisher information for hierarchical model, like neural networks, is only positive semi-definite. The Fisher information can thus be rank deficient at singularities, and ordinary gradient descent may fail to learn and very slow to converge close to singularities. Recall that the ordinary gradient descent updates the current parameter by scaling the gradient of the energy function with a step size called the learning rate. The natural gradient descent extends the gradient descent to parameters belonging to Riemannian manifolds by scaling the ordinary gradient by the inverse of the metric tensor at current location. The natural gradient is invariant to reparameterization and is proven to avoid plateau phenomena observed near singularities by ordinary gradient descent. We shall now explain the fundamental geometric structure of information geometry, which consists of a dual structure extending the Fisher-Rao manifold, which we shall see is self-dual. This dual structure allows one to explain the duality between statistical inference, like the maximum likelihood, and a family of principal statistical models, like the exponential families that we obtain from maximum entropy distribution, with respect to Shannon entropy. We shall introduce the second principle of invariance in information geometry, which is invariance by sufficient statistics. That is, invariance by considering the sample space. This novel generic dual structure opens new perspectives in information sciences and complex systems, and has found many applications ranging from signal processing to medical imaging and machine learning and AI. First, we shall give a general definition of the concept of geodesics in differential geometry. We said earlier that Riemannian geodesics are locally length minimizing curves. In general, geodesics are the straight lines with respect to an affine connection nabla. Geodesics are said to be nabla autoparallel curves. This nabla is also an operator that is called the covariant derivative of a tensor field T by a vector field X. To define an affine connection nabla on a d-dimensional manifold, we need to define d-cube functions that are called the Christoffel symbols. In Riemannian geometry, we use an affine connection by default, which is called the Levi-Civita connection, and this Levi-Civita connection can be instantiated from the metric tensor G. Here, I show the Christoffel symbols for the Levi-Civita connection derived from derivative of the metric tensor G. The curvature of a manifold is defined by the affine connection. Here, I show two 2D manifolds embedded in the Euclidean 3D space. I show the parallel transport defined by the affine connection on loops. On the cylinder, we see that the nabla parallel transported red vector goes back to its original black vector position after circulating on the loop. The curvature of the cylinder is set flat. On the right figure, we see the parallel transport along a geodesic triangle on the sphere. We can observe that when we come back to the original black vector position, the red vector makes a non-zero angle with the black vector. This attests the presence of curvature. The sphere has positive constant curvature. An affine connection is set flat if we can find a coordinate system θ such that all the Christoffel symbols expressed in this coordinate system θ vanish. In that case, the geodesic ordinary differential equation simplifies and its solution is a line segment. Geodesics with respect to flat connection are line segments in the θ coordinate system, and moreover, the parallel transport with respect to a flat connection is path independent. We now define the core geometric structure of information geometry, a quadruple M, G, nabla, nabla star, which consists of two torsion-free affine connections, nabla, nabla star, which are dually coupled to the metric tensor in the sense that their average connection is a Levi-Civita connection. The fundamental theorem of Riemannian geometry states that there exists a unique torsion-free metric-compatible connection, precisely the so-called Levi-Civita connection. Metric-compatible means that the inner product between two vectors does not change when we parallel transport this vector using the Levi-Civita connection. Dual information geometry manipulates dual connections such as the inner product between the parallel transported one vector with respect to one connection nabla and the parallel transported second vector with respect to the dual connection nabla star, is invariant. The metric is preserved by this dual parallel transport. Moreover, duality is involutive. The dual of a dual affine connection is a primal connection. So the question is, how can we find meaningful dual connection? We shall see two standard methods. The first one is the expected alpha connections of Amari and Nagaoka, and the second method is the method of Eguchi, which builds dual connection from a smooth parameter divergence. This second method yields what is called the divergence-based information geometry. Let us explain the alpha geometry, which is the dual information geometric structure with the alpha connection and minus alpha connection. The formula to calculate the Christoffel symbols of this alpha affine connection is shown here. It relies on the expectation with respect to the statistical model. The minus alpha connection is dual to the alpha connection with respect to the Fisher information metric. There are some special affine connections from this parametric family of affine connections. The zero connection is just the Levi-Civita connection corresponding to the Fisher metric. The one connection is called the exponential connection and was pioneered by Chernoff and Efron. The minus one connection is called the mixture connection, or nabla M, and was reported in a comment to Efron's statistical curvature paper by Derwig. Let us now see a second method to build meaningful dual information geometric structures, the divergence information geometry. Eguchi's method consists in taking a divergence D, also called a contrast function, for example the Kullback-Leibler divergence. In general, notice that the statistical divergence between two parametric densities corresponds to a parameter divergence. Eguchi defines a metric tensor induced by a divergence D by the following set of partial derivatives. Similarly, he defines a connection induced by the divergence D, nabla D, by these third-order derivatives. Let us now define the dual divergence as a divergence on swap parameter order and build the affine connection corresponding to this reverse divergence. Then you can show that this affine connection, nabla D and nabla D star, are dual to each other with respect to the metric tensor GD. Notice that when the divergence is symmetric, the forward and backward divergences are identical, and the divergence information geometry is self-dual in that case. The relative entropy, also called Kullback-Leibler divergence, belongs to a wider class of distortion measures called the f-divergences. A f-divergence between two densities P and Q is defined for a convex generator function f, which is strictly convex at 1, as a definite integral of P f of Q over P. We can fix without loss of generality f prime of 1 to 0 and scale the f-divergence, so f prime prime of 1 equals 1. We get the so-called standard f-divergences. F-divergences may be asymmetric. We get the dual or reverse f-divergence by choosing the generator f star equals u f over 1 over u. The metric tensor induced by the dual f-divergences by Eguchi method corresponds to the Fisher information metric, and the dual affine connections induced by the dual f-divergences correspond to Amari and Nagaoka expected alpha connections with a value of alpha depending on f as follows. An important concept of information geometry is the information monotonicity. Consider a transformation y equals t of x between two measurable spaces. The second principle of invariance of information geometry states that neither the Fisher information nor the statistical divergences D should increase by transforming the random variable xi to the random variable yi. Moreover, equality only holds if the transformation T is a sufficient statistic. A sufficient statistic summarizes all necessary information for statistical inference without loss of information. That is, the probability of x knowing theta should be equal to the probability of x knowing t. A theorem characterizes all information monotone divergences which are separable as f-divergences except for the very special case of binary sample space alphabets. The family of probability distributions having finite dimensional sufficient statistics are the exponential families. The canonical densities of parametric distributions of an exponential family write proportionally as an exponential of the inner product of the natural parameter θ with a sufficient statistic T of x. Let f of θ be the log normalizer so that the densities of an exponential family integrate over the support to 1. The log normalizer f of θ is also called the log partition or the cumulant function and is probably strictly a convex function which is real analytic. Many familiar distributions, like the categorical distributions or the multivariate Gaussian families, are exponential families once the ordinary parameterization is changed to its natural parameterization, θ. The information geometry of an exponential family is a dually flat space. That is, the plus or minus 1 expected connections, also called the exponential and mixture connection, are dual to each other with respect to the Fisher metric. And moreover, these two E and M connections are flat, whatever the chosen exponential family. An exponential family is said regular if its natural parameter space is topologically open. For regular exponential families, we can define the dual moment parameters eta, which equals the expectation of the Fisher statistics. When the log normalizer f of θ is of Legend type, we have a one-to-one correspondence between the natural θ and the moment parameters eta. The Fisher information matrix of an exponential family can be expressed either as the Hessian of the log normalizer with respect to θ, or the Hessian of the convex conjugate function f star of eta with respect to parameter eta. These two Fisher information matrix expressions, multiplied together, always yield the identity matrix. Dually flat spaces are manifolds with global Hessian structures. In general, a dually flat space can be built from any Legend-type strictly convex function f of θ. These convex functions can be built from statistical models, like the cumulant function of exponential families, or minus the Shannon entropy of mixture families in information geometry. In a dually flat space, the primal and dual geodesics write as line segments in the primal and dual coordinate systems. Moreover, in a dually flat space, there is always a canonical divergence, which is a Bregman divergence. This Bregman divergence can be obtained from the log normalizer of exponential families and amounts to a reverse Kullback-Leibler divergence. Usually, the converse is shown analytically, that is, that the Kullback-Leibler divergence between two densities of a regular exponential family amounts to a Bregman divergence. However, information geometry gives a principal way to reconstruct the statistical divergence, here the reverse Kullback-Leibler divergence, from the convex parameter function f of θ via the Bregman divergence. We can visualize the Bregman divergence by graphing the function f of θ. The vertical gap between the points θ1, fθ1 and the linear approximation of f of θ at θ2 evaluated at θ1 represents the Bregman divergence. The concept of Bregman divergences was introduced in the 1960s with the concept of cyclic Bregman projections for finding a common point in a non-void intersection of convex objects. By using both the primal and dual parameters induced by the Legend-Fenchel transformation, we can express the Bregman divergence as the following Fenchel-Young divergence, yff star. Notice that the equality holds if and only if eta2 equals the gradient of f at θ1. This is the so-called Fenchel-Young inequality otherwise. For Legend-type functions, there is a one-to-one mapping of primal to dual parameters, and the gradient of the convex conjugates f of θ and f star of eta are functional inverse of each other's. Thus, by using a combination of primal θ and dual eta parameters, we end up with the following identities of a Bregman divergence. First, we can express a Bregman divergence as an equivalent dual Bregman divergence on swap parameter order. Then, by using the equivalence between the Bregman divergence and the Fenchel-Young divergences, we get this equality boxed in red here. In general, a formula with n terms in a dually flat space can be expressed equivalently in 2 to the n way different by considering each term either expressed in the primal or its equivalent dual parameterization. A key geometric theorem in dually flat spaces is the generalized Pythagoras theorem. When a primal geodesic meets a dual geodesic at a point Q, we get the following three-point identity. We can therefore test whether two curves intersecting at a point Q are orthogonal or not by checking that the scalar product θ1 minus θ3 dot product eta2 minus eta3 equals 0 or not. When the potential function f of theta is chosen as half of theta squared, we get the Euclidean geometry with the corresponding Bregman divergence yielding the half of the square Euclidean distance. In that case, the generalized Bregman-Pythagoras theorem becomes the usual Pythagoras theorem here. In optimization problems, we seek to characterize whether the solution is unique or not. The generalized Pythagoras theorem will prove useful to demonstrate the uniqueness of information projections in special cases. Define the E projection or exponential projection of a point P onto a submanifold S by considering the E geodesic passing through the point P, which is orthogonal to submanifold S. When S is a n-flat, meaning that in the dual parameter space it is an affine subspace in the eta coordinates, we get uniqueness of the projection. The proof of uniqueness relies on the generalized Pythagoras theorem. Similarly, the M projection of a point P onto a E-flat is unique. Moreover, using the canonical Bregman divergences, we can show that these orthogonal E and M projection correspond to minimizing Bregman or dual Bregman divergences. Let us illustrate these unique projection theorems in statistics. Consider identically and independently samples x1 to xn, and let their empirical distribution of this random vector be the observed point on the manifold. The maximum likelihood estimator for parameter θ of an exponential family can be interpreted as the mixture projection or M projection of the observed point to the E-flat defined by the exponential family. Thus, by the uniqueness of the projection, we know that the MLE is unique. Here, the MLE corresponds to minimizing the Kullback-Leibler divergence between the empirical and the model distribution. By analogy, we can define statistical estimators from divergences by similar optimization process. We seek special divergences which yield good properties of estimators, like for example robustness to noise or contamination, or allow us to handle unnormalized model densities. Similarly, the maximum entropy principle, which seeks to maximize channel entropy under moment constraints, yields an exponential family with the sufficient statistics given by the moment constraints, and this can be interpreted as a E projection or exponential projection by following a E geodesic. This maximum entropy problem amounts to minimize the reverse Kullback-Leibler divergence of a uniform distribution to the M-flat of distributions satisfying the constraints. The set of constraints define a M-flat, and by projecting the uniform distribution along an E geodesic on this M-flat, we get the distribution with maximum entropy. For example, the maximum entropy distribution with prescribed first and second order moments yields the family of normal distributions. Yet, another useful method often used in statistics and information theory is the alternating projection algorithm, or the lowercase EM algorithm, where E stands for exponential and M for dual mixture connection. The EM algorithm solves iteratively the minimum divergence between two submanifolds P and Q. When P is M-flat and Q is E-flat, we start from a point Q1 in Q, and then we E-project it onto a submanifold P, and then we project this point onto submanifold Q by an M projection, and so on. The alternating projections probably converge to the minimum divergence between these two submanifolds. The lowercase EM algorithm is useful for interpreting expectation maximization algorithm, the uppercase EM algorithm, in statistics, or to analyze generative models in deep learning, like variational autoencoders, VAEs, or generative adversarial networks, GANs. Actually, as I quickly mentioned earlier, the definition of Bregman divergences was motivated by some problem in operations research. We are given a finite set of n convex objects in some coordinate system theta, and we wish to find a common point in their common non-void intersection. The Bregman cyclic projection algorithm starts from an initial point and projects onto the first object by minimizing the Bregman divergence, and then projects this new point onto a second object, the second constraint, and so on, by taking a Bregman minimization problem. The constraints are taken into cyclic order. When we reach the last constraint, the next constraint will be the first one, and so on. This cyclic Bregman projection algorithm probably converges in the limit to a common point intersection, but only in the limit case. Let us see now the powerful framework of information geometry for some problem in statistics. We are given n independently and identically distributed variates, x1 to xn. They emanate from a balanced statistical mixture model, which is 1/2 of P1 plus 1/2 of P2, and we have to design a rule to classify these samples. We inherently make mistakes when the support of distribution P1 overlaps the support of distribution P2. Chernoff shows how to bound this probability of error in Bayesian hypothesis testing for the base rule, which is the maximum a posteriori rule, or the map rule. When P1 and P2 belong to the same exponential family, we can show that the Chernoff exponent alpha star, which characterizes the Chernoff information, is the intersection of a M bisector with a E geodesic, and that this intersection is unique. Thus, although it may not be computationally tractable to compute the Chernoff divergence, or the Chernoff information, we can always geometrically exactly characterize this Chernoff information distribution. When instead of two distributions we get a finite set of n distribution, the n-array Chernoff information is defined as the closest pairs of distribution with respect to Chernoff information. On the left, we visualize n distribution is a probability simplex of categorical distribution. On the right, we show the n density of an exponential family on an exponential family manifold. To compute the closest pair with respect to the Chernoff divergence, we can calculate the Kullback-Leibler Voronoi diagram, which amounts to a Bregman Voronoi diagram. Therefore, many techniques of computational geometry can be fruitfully used to solve a problem in statistics. We have already explained the benefits of natural gradient compared to ordinary gradient for optimizing where the parameter space has a manifold structure. When the parameter space is a dually flat space or a Hessian manifold, we can show that the natural gradient with respect to the primal parametrization theta amounts to an ordinary gradient descent with respect to the dual parametrization eta. This observation, which can be proved simply using the chain rule derivation, is very useful in machine learning and AI. For example, this property can be used in natural evolution strategies, NES, or also in Bayesian inference, and so on. To summarize this tutorial on the classical structures of information geometry, let us say that information geometry seeks geometric structures of statistical models which can either be parametric or non-parametric. Here, we have only considered parametric models. We have mentioned two basic invariance principles. The first invariance is invariance under reparametrization of the parameter indexing the statistical model. The second invariance principle is information monotonicity of Fisher information and monotonicity of statistical divergences under Markov morphism on the sample space, with the information being preserved if and only if the transformation is sufficient. We then explain the Fisher-Rao manifolds, which use the Fisher metric induced by the Fisher information matrix and use the Riemannian geodesic length distance called the Rao distance. We show that this Fisher-Rao structure can be extended by considering a pair of torsion-free affine connections which are coupled to the Fisher metric, and we get the alpha geometry, with the zero geometry recovering the Fisher-Rao structure. We also explain the construction of Eguchi to get a dual structure from any divergence. The dualistic nature of information geometry allowed to reveal the interaction between statistical estimator, like the maximum likelihood estimator, and statistical models, like exponential families, which arise from the maximum entropy principle. We describe a generalization of the Pythagoras theorem, which allows us to characterize interesting cases where information projections are unique. Thank you very much for your attention. Below you find some book covers of textbooks or edited books dealing with information geometry or geometric modeling of statistical models. I would like to take this opportunity to advertise the recent edited Handbook of Statistics, volume 46, which deals with geometry and statistics. Professor Fisher-Rao is turning 102 years old next September. Here is a list of references related to this tutorial. The book of Professor Amari does a great job in explaining the essence, structure, and application of information geometry. I also wrote a very short article summarizing in less than 10 pages this tutorial for the AMS notices. The information geometric viewpoint of Chernoff information is described in this letter, and Bregman Voronoi diagrams have been studied from the viewpoint of computational geometry in this article. Last, let me mention two recent works with my collaborators on natural gradient here.